is on the VSEPR theory. We're going to learn about two um, ways that we are able to look at our Lewis structure and predict the geometry of our molecule. And one is hybridization and the other is VSEPR theory. Well, we're going to focus on VSEPR theory today. VSEPR is actually an acronym that helps us remember the first key letter of each word in this theory, and that is the valence shell electron pair repulsion theory. Now remember, when we draw our Lewis structures, our electrons come in pairs. One electron spinning clockwise, the other spinning counterclockwise when you go back to your spin quantum number. But those valence electrons are the ones that are being involved in bonding, and they're the ones that they repel each other. So when you're applying this theory we call VSEPR theory, it is based on the assumption that your electron pairs repel one another, thus the name valence shell electron pair repulsion theory. So what happens is the electrons pairs try to get as far apart as possible around your central atom. They're going to push and repel one another within the space available. So the geometry, or what we call the shape of your molecule, depends on the number of electron pairs around your central atom. And in our notes, I'm going to abbreviate central atom CA in our chart that we're going to make in our notes in just a second. Now you must first draw the Lewis structure. You must draw your Lewis structure first, and then you will predict your geometry using VSEPR theory. So in the handout that I gave you for your notes, there's a table. The headings say molecular shape or VSEPR shape, number of atoms on the central atom, number of lone pairs on the central atom. Remember, the lone pairs are the dots that we draw. And then I'll give you an example. All right, so linear is our first VSEPR shape that we want to look at. And so if you have two atoms on your central atom and no lone pairs, so like if we draw a molecule of carbon dioxide, this is what our Lewis structure would look like. You'd have carbon in the middle. You would end up having double bonds on each side of carbon connecting to your oxygens, and the oxygens would have 4 dots on them. Okay, this will give the octet for each atom present. Well, if carbon is your central atom and there's no dots on the carbon, so here it says number of lone pairs on the central atom, there's no dots on the carbon here. So for these molecules or these atoms to get as far apart as possible, they're going to get in a straight line around this central atom carbon. So the bond angle here for this is going to be 180 degrees. So over here, make sure you label that bond angle as 180 degrees. That's our first VSEPR shape, linear. Now, if you were to add to the mix some lone pairs, so we still have 2 atoms on the central atom, but now let's put some lone pairs there. So like with water, when you draw a water molecule, draw its Lewis structure. Now more than likely when you draw this, you would, on your paper, you would have drawn it more like this, because you wouldn't know right now at this point that it was going to be bent. And I'm not going to require y'all to redraw them so they look bent. So yours on your paper would look like this. So when you're trying to decide the VSEPR shape, you would look at your central atom, and which is oxygen, and you notice there's 2 atoms attached to the oxygen. So that's where we have the 2 atoms on the central atom. But you also have lone pairs. You have, these are your lone pair electrons here and here. Well, those lone pair electrons push on those hydrogen-oxygen bonds, and it pushes them down into this angle. So we can call it bent or angular. And the bond angle for this particular VSEPR shape is 105 degrees. Now technically it's 104.5, but we'll just remember 105 degrees. Now the third VSEPR shape involves when you have 3 atoms attached to your central atom and no lone pairs. So like with boron trihydride, this is going to have to be what you have for your Lewis structure. And you might think, well, wait a second, Ms. Danks, boron doesn't have his octet rule satisfied. Well, remember in the notes we said that boron and beryllium were 2 of our exceptions to the octet rule. Let me just explain to you why this has to be the VSEPR shape. When you add up your valence electrons here, boron, because he's in group 3A, he has 3 valence electrons. And the hydrogens, there's 3 hydrogens, but they only have 1 apiece. So when you add this together, there's only 6 electrons between all 4 of these atoms. So when you connect the hydrogens to the boron with a single bond apiece, 2, 4, 6, you have used all 6 of your electrons. So there are none left to distribute to the boron. The hydrogens have nothing to loan him. So he has to settle for the 6. So he's one of our exceptions to the octet rule. Now, when you think of 3, like the geometry, you think of a triangle. So the name of this VSEPR shape is trigonal or trigonal. Think of a triangle. And this is a flat molecule. The bond angles are equally spaced. So your bond angles here are 120-degree bond angles. Our next VSEPR shape is what I call a cousin to trigonal planar. And it's going to have 3 atoms on the central atom and 1 lone pair of electrons. So here we have with ammonia NH3, nitrogen trihydride. Notice you have lone pairs on the nitrogen. So you have your 3 atoms on the central atom. There's your triangle, trigonal. And the lone pairs here are going to push those hydrogen bonds down into a pyramid shape. So it looks like this. And your bond angle here is going to be 107 degrees. Finally, tetrahedral. Remember, tetra means 4. So 4 atoms on the central atom and no lone pairs. Now when you draw this on your paper, it's going to look like these are 90-degree angles. But remember, y'all, our molecules are 3-dimensional. They're not flat all. So you have to keep in mind the 3-dimensional quality of them. So the bond angles here are not 90. They can get even farther apart than that. The bond angle on tetrahedral are 109.5 degrees. Now I have attached a simulation to your Edmodo for you to use. And so that's what we're going to look at real quickly with the last little bit of this. And then we'll look at some examples. So the simulation that I want us to look at is a PhET simulation. And it is going to be modeling your molecular geometry. Man, my computer's just going crazy today. Sorry about that. All right, so if you take a look here at this, I want you to notice, like if we were going to do just like carbon dioxide, we looked at that one. So carbon's your central atom. I'm adding 2 oxygens to it. Notice here, if we look at the molecular geometry, you will, and I'm going to show the bond angles. You'll see the bond angle is 180. Even if I kind of throw this molecule around and swing it around, as soon as I release it, the bonds spring back to 180 degrees. They're pushing as far apart as possible. Now I'm going to remove 1 pair of the double bonds here, and let's just add some lone pairs. These are our dots that we draw, and lone pairs take up more space than the regular bonding electrons. So if I add some lone pairs here and here, notice what happens. You get this kind of an angular shape. And I'm going to remove the lone pairs for a second so you can see the result. This looks linear, 180 degrees, but watch what happens when you put the lone pairs. They bend the molecule. And that's that trigonal planar structure. It was called planar because it's a flat molecule. Like if I try to turn it where it's flat, see, it's a flat molecule, trigonal planar. So attach this to Edmodo for y'all to continue to kind of play around with. I'm going to attach another video that is going to have some more examples on it as well.